to have Jian Ding here, and he's going to speak to us about recent progress on random graph matching problems. Jian, over to you.
Okay, thanks, Christina, for the invitation. It's a pleasure to speak here. It's 10 p.m. in my time zone, so I might sound a little not energetic, but that's probably would help in terms of giving a light talk without too many technical details, because I can't really think clearly at this point. The talk is based on joint works with a bunch of students from Peking University. Hangdu is an undergraduate student in his senior year. Shuyang Gong is a second year PhD student. Zhangsong is also an undergraduate student in his senior year. Okay, so the purpose of this talk is to explain what are the motivations for studying graph matching problems, and what is the idealistic model that people have been focusing on up to this point, and what the community has, what progress the community has obtained, and along the way I will also explain what contributions we have made. I will also explain some of the future directions toward the end. So that was the plan. We can imagine the following scenario. We have LinkedIn and Twitter, both are social networks. LinkedIn is for job search. So this is usually this is a network with real names and usually with the real information. Twitter is it's a platform for us to complain about various things, and typically people choose to be anonymous. Roughly speaking, that's the situation. Now we can imagine each individual, their friends in both networks should have large overlaps because it's the same person. As a result, these two networks should be similar to each other. And if we can use this similarity to match the individuals in both networks, then the presumably anonymous Twitter network becomes not anonymous, right? So this is actually a bad application of graph matching, as this would violate the data privacy. I will also explain later, if we switch the perspective, suppose we want to be a data protector, this actually would motivate some very nice theoretical questions, but I will explain that a bit later. Now let's imagine another scenario. I think this is a scenario that we want to study the interactions between proteins in a cell. Say we take the human network and the mouse network. Despite the fact these are two very different species, if we look at the similar type of cell, the functions of the proteins should behave similarly. And as a result, we can imagine that the network arising from these interactions of proteins should be similar to each other. And if we can match these networks, then we would be able to translate our knowledge, say, from the mouse network to the human network. This is clearly useful because for mouse, we can perform extensive studies and experiments. And for humans, it's much more expensive and much harder, and also it involves ethical issues. And this way, we can translate our knowledge from mouse to humans. Yet another scenario is in computer vision. A fundamental problem in computer vision is to detect an object. An object is actually a bit easier because usually an object, the only difference in different pictures is the angle and maybe also the light on how the lecture was taken. But for humans, this is much more complicated, as human can have many different gestures. And if we look at these pictures in terms of the pixels, they could be very different, but we still want to detect them as the same object, right? They're both individuals, whether they stand or whether they bend them, whether the person bends. One possibility is to construct a network from the human body. We can use we can divide the human body into many pieces of regions, and the neighboring regions, we put an edge between them. We can imagine that no matter what the gesture is, the topology of the network is more or less stabilized. And as a result, if we can match these networks in two pictures, we can sort of imagine that these two probably would refer to the same object. Of course, I'm only explaining this very basic and rough idea just to show you why this graph matching problem is relevant in these problems without claiming being accurate at all. There's yet another application about machine translation. This is very similar to the application 2 in biology I just mentioned. It's like a similar thing, but presented in a different manner. We have words in different languages. If we can match their interaction of these words, and then, okay, the corresponding words should have the same meaning, and this serves the purpose of translation. Okay, I believe I give you enough relevant background to motivate the study of graph matching problems from the application point of view. Of course, in each of these applications, what I said is we need a model, right? We need a precise mathematical model to study these things. And what I just said is not able to capture it's not able to capture any of this network, but they captured something of this captured something in common of these problems, and that's what we want to study theoretically in this talk. Now let's formulate a precise mathematical question. What do we want to do? Basically, the question can be formulated as follows. We have two graphs, and we want to match their vertices. That is, well, we want to assign labels to both graphs so that these two labeled graphs, and if we look at the intersection or the common graph, we want the number of edges to be as large as possible, right? This is now an optimization problem. We have two graphs. We want to match, say the two graphs, they have the same number of vertices. We want to match their vertices so that they have the largest number of common edges. Unfortunately, this optimization problem is very hard. It's NP hard, which means, well, unless we can solve some big problem like P equal to NP or not equal to NP, and there's no hope that we can solve this problem in its worst case. We do not plan to attack P not equal to NP in this talk, so we want to set a more modest goal. How we can do that? Well, these computational problems are very difficult, usually for worst cases. But we are looking at realistic problems, and these problems should arise at some random fashion. And as a result, we could work with some probabilistic model and see whether in a typical scenario, we would be able to solve the problem, okay? So that is, for that, we would like to have a probabilistic model for the random graphs, right? Actually, for a pair of random graphs. There are many choices. Of course, we would like to choose those random graph models that can capture the truth, capture the scientific problem or the realistic or the real world problem as much as possible. But as we all know, in theory, when we want to start developing some mathematical theory for these problems, we usually choose some canonical and simple model to begin with. And a typical choice is the Shuyang graph. And the Shuyang graph is just where we have n vertices and we put an edge with probability P independently between each pair. But we want not just one Shuyang graph, we want a pair of correlated graphs. How can we do that? One possibility is we first sample a mother graph, which is Shuyang, and then from the same mother graph, we independently subsample two subgraphs. And the subsampling is also very simple. For each edge in the mother graph, we keep it with the probability S independently. So now we get two subgraphs they are conditionally independent, but since they depend on the same random matter graph, they are correlated unconditionally. Okay, at this moment, these graphs have the correct vertex correspondence. That's not the observation we usually have. Usually what we observe is either unlabeled graphs or equivalently, graphs with the labels randomly permuted. Okay, so our observation is the two subgraphs we see at the right end of this picture. In this model, there's no structure in the randomness. The edges just show up independently. I mean, I think actually this audience is familiar with the Shuyang graph. I don't explain this. The advantage is, well, it's simple. It's a suitable playground for developing mathematical theory. The disadvantage is also clear. Almost all realistic networks are not Shuyang, but as I said earlier, this is usually the starting point to build mathematical theory for difficult problems. Already we will see, even for this very simple and very idealized model, this question, it seems to be very challenging. Okay, now let's see what are the interesting questions we want to study. There are two types of questions for graph matching. One is information theory, one is computational aspect. From an information theory wise, we want to see whether there's enough signal to do anything, right? That's the first question we should ask ourselves. Otherwise, if there's not enough signal at all, well, there's no bother to make any effort. So, okay, so let's look at the information theory. Usually, in my presentation so far, I just assume that the two graphs are correlated and we want to match the vertices. But actually, a question before that usually should be to decide whether two graphs are actually correlated or not. So this is a hypothesis testing question. For instance, the null hypothesis could be, well, we have two independent Shuyang graphs. And the alternative hypothesis is we have two correlated Shuyang graphs produced in the way I just described. This is the detection problem. And if there is indeed correlation, then we can try to match the vertices exactly, or we can just try to say, correctly match 10% of the vertices. That's what we call a partial recovery. On this, Wu, Xu, and Yu in 2020 and 2021, they made very good progress based on maximal common graph. When the average degree is order 1, Ganasali, Masolia, and Lalarge also made very good progress. I will focus more on the work of Wu, Xu, Yu because that's closely related to what we did. Also, that covers a wider regime for the graph parameters. Their statistics is very simple. It's actually the natural one, what you would imagine. You just look at the maximal common graph over all the bijections. If the so pi hat is this bijection that maximizes the number of common edges. If the number of edges is large in this common graph, then while we say these two graphs are correlated, we can also just use this optimal bijection as the estimate of the ground truth. In this manner, the results Wu, Xu, Yu obtained is that they can determine the exact recovery threshold, and for detection and partial recovery in the dense regime, where dense means p is equal to n to the power of liter of 1. In this regime, they can also get the exact threshold. But in the non-dense regime, that is when p is a negative power of n, they can only determine the information thresholds up to constants. And why is this? This is related to the analysis. I feel that it's a chance that this statistics is actually should give you the sharp threshold, but the way they analyze it, they lose they lost some information. Why is that? One key ingredient in their analysis is to lower bound the number of common edges in this pi hat, right, in this maximal bijection. But that is something relatively hard to analyze. Alternatively, they just choose to lower bound it by the number of common edges in the ground truth. And I think this actually loses something which leads to this gap when the graph is not dense. So with Hangdu, we improved this and we obtained the exact thresholds, exact detection thresholds in the non-dense regime. How did we do it? Well, we could try to improve their analysis, but that seems to be quite difficult because one has to take into account of the irregularity issue for the common graph on the that analysis is difficult because this maximization, you would have to do very difficult second moment computation to get a low bound. Okay, let me put it this way. But we are doing a hypothesis testing problem. We have the freedom to choose the statistic. We don't have to choose the maximum common graph, actually. We can make a little modification. And what we choose is, instead of looking at the maximum common graph, we look at the densest subgraph under the optimal bijection. That is, well, actually, we look at the densest subgraph with the size larger than, say, n over a billion. And we maximize over the subgraph and also maximize over the bijection. Okay, I should have said earlier, neither of this statistic is computable, right? This optimization problem is very difficult. This is why this does not give an algorithm. It's only give a information theoretic analysis, okay? Having said that, let's see why looking at density subgraph would be much better. Let's stick to the ground truth. Let's stick to the pi star. And we look at if we look at the pi star, that's the ground truth. The common graph is an Ardashirani. And near the threshold we consider, this is actually the Ardashirani graph with average degree. Ardashirani graph with average degree has fluctuations and irregularities. The degree has fluctuation, right? In particular, we would have many isolated points. That's why when I said, when we use pi star to estimate pi hat, we lose something because on these isolated points, we did not get any edges. So we should try to re-optimize over these isolated points at least to pick up something there. And the actual optimization should be much more complicated than that, which is a bit harder to analyze, as I suggested earlier. What we did alternatively is, okay, now we have this at the Shuyang graph. We look at the densest subgraph. The average degree in the densest subgraph is actually larger than the average degree of the whole graph. As a result, we get more information. And it turns out this is all the information you can get. One crucial input is we need to analyze this densest subgraph. For instance, we need to know how to compute the average degree of the densest subgraph in Ardashirani. Happily, this has been done in 2016 by Anatharam and Salas. And this question actually has to do with the load balancing questions that has been studied by people in related but sort of different communities. Also, in their solution to this problem, they use this objective method invented by Ados and Steele. It's a very beautiful paper. Anyway, they can compute the average degree for the density subgraph, and that is a cornerstone for our proof. The main intuition why this is better is that the average degree of the maximum common graph in independent case, it does not increase by taking subgraph with the linear size. So now we have, in the correlated case, if we just take the ground truth, this thing is increased, but in the independent case, this does not increase. This separation gives us additional information, and this helps us. So I said all of this to say why density subgraph is a much better statistic. Actually, to prove it is, it can only take 1 page, provided with the result of an theorem and silence. It's just a simple computation. We just need to upbound the maximum density subgraph in the independent case. That's just the first moment with a little bit of clarity. It's not the most straightforward, but a little bit of work, half a page of calculation would be enough. Much of the technical and difficult work goes to prove the impossibility regime. We need to show that below the threshold, there is no way we can detect it. For this, we need to show two probability measures are close to each other. And the typical way is to show that, well, there are 2 ways, roughly speaking. One is to show some sort of KL divergence of the 2 measures small. Another one is to compute the likelihood ratio and control the second moment. Here it seems more natural to compute the second moment, but the second moment blows up, as in many cases, because if some real event happens, this likelihood ratio is very big. It turns out, well, okay, usually in these cases, what saves us is some suitable truncation, right? It turns out the suitable truncation is exactly to put conditions on the density subgraph of this common graph. So in this way, the upper bound and lower bound, they matches because they rely on something that is in common. Okay. I will not explain the technical details any further. I hope this gives you enough flavor of what's going on. Also, along this line and doing more work, perhaps significantly more work, we were able to also obtain the exact partial recovery thresholds in the non-dense regime. So we improve both. So we close the gap that is left by Wu, Shu, and Yu. At this point, I would say, at least I'm more or less satisfied with our understanding from the perspective of information theory. The main challenge of this topic is on the computational aspect, which I will describe in what follows. So now let's pretend we are not statisticians, but we are, say, computer scientists. For statisticians, usually there is a signal and we want to find it. But for computer scientists, we want to do optimization, right? And we don't care about whether there's a signal or not. And actually, we can just take 2 independent Shuyang graphs and say, okay, find a efficient algorithm to maximize the overlap, how well we can do. This is a very natural question. And this is also a question that is in one example in a broad class. We have many NP-hard combinatorial optimization problems, and then we can take a canonical random instance and ask what we can do for a typical sampling of this problem. With the Hangdu and the Shuyang Gong last year, we found a p-test, a polynomial time approximation scheme when alpha is between 1/2 and 1. Why alpha is between 1/2 and 1? Well, when alpha is equal to 1/2, it's a little subtle. We were not able to analyze it. And when alpha is below 1/2, this is very dense. As a result, the large deviation effect is very strong, which means no matter which bijection you take, the first leading order is more or less the same. It doesn't change. There's nothing much you can do. And that's why we focus on the regime when alpha is between 1/2 and 1. I should explain what is p-test. There is a theoretically optimal value, which is the 2 alpha minus 1 to the inverse power times n. This is the asymptotically the sharpest you can do from probabilistic point of view. A p-test means giving any small epsilon, there exists a polynomial time algorithm where the power depends on epsilon. And in this case, actually, it blows up as epsilon goes to 0, so that it finds a overlap that is 1 minus epsilon large times the optimal value. What I should mention is this theoretical value. It was not known from a non-algorithmic point of view. So what is the usual method to lower bound the maximum of stochastic processes? There are usually two ways, right? One way is to compute the second moment, first moment, second moment, and say, okay, we do have some very large points. Or another, in this case, it seems a second moment computation is quite difficult. We tried that pretty hard, actually. We didn't manage still. Alternatively, there's a constructive method. We can try to build something. We can try to find the variable depending on the environment. If we can cook up some algorithm, some construction that finds the variable that achieves near if not achieve the maximum, but achieves near the maximum, and that's also good enough. In this case, it seems this constructive way to prove a lower bound on this maximum overlap seems more efficient. Then that's something sort of interesting. Usually we feel a algorithm would come after the information theory, but for this particular question, it's not the case. Also, the algorithm is pretty simple. It's iterative, or actually just kind of greedy algorithm. We check sequence of points. We just look at points one by one, and we try to, or in small groups, group by group, and we try to do some locally we try to do some greedy fashion of matching. The algorithm is simple, but the analysis is very difficult. The difficulty is common for most other iterative algorithms in a random environment. We need to control the correlations between different iterative steps. There are usually two ways to control the correlation. One way is to say, okay, the correlation is small in absolute value, and as a result has little influence to what we want to do. Or the second way is to say, okay, I don't know how to control the magnitude of the correlation, but it's always in the direction that is in our favor. For instance, if we have FKG, we apply it, that's fine. In our analysis, we have to use both. Sometimes we have to say the correlation is small in absolute value. Sometimes we have to say, okay, we can apply FKG. And we have to be very careful that we can separate these two correlations and have a working proof. That's why this is difficult as far as we can tell. Okay. Finally, let me comment that I said it was trivial for alpha less than a half because no matter what you do, the leading order is the same. But in that case, you could try to optimize the second order term. That turns out to be an interesting question. A group of students at Peking, they are working on it, and they seem to be able to show there's some sort of computational phase transition for that question. Just as a side remark, this is one of a few examples where a random optimization can be solved, but what's the case is NP hard. And there are some other examples like in spin glasses. More or less, these things morally, this seems to rely on some sort of full replica symmetric breaking sort of picture. There's something like that underlying the success of these algorithms. Except for this one, it's less clear. In some of the other ones, it's more this connection is more transparent. And finally, I want to remark that actually we discussed this question with Wu and Xu from a non-algorithmic point of view, where we tried to do second moment, but we failed. One of the motivation for Wu and Xu to propose this question is that they feel this may be related to overlap gap property for correlated graph models. Overlap gap property is some sort of criterion that give you an evidence for the hardness of the computation. Actually, these days is fairly widely received, so it's something quite interesting. I will come to that again a bit later. Okay, so this is about the optimization problem when the two graphs are independent. However, when the two graphs are correlated, this is much more difficult. The algorithms we used, forget about analysis, would not make sense. So this is when there is correlation, and how we can, in this case, whether we can maximize the common graph. This is a harder problem, and much harder problem, and many people have made extensive efforts. And now I want to report to you the progress the community collectively obtained on this problem. So now let's assume that we have indeed two graphs that are correlated with each other, and we want to match them. Clearly, if the correlation is higher, this problem should be easier, right? Because the signal is stronger. How can we match two graphs? Well, we can imagine there is one approach is we compute a signature. For each vertex in each graph, we compute a signature. And then we take we take a pair of vertices and compare their signatures. If they're similar, we can say, okay, this is a true pair. If they are not similar, then they are a fixed pair. This seems to be very reasonable, right? A good framework. And well, what are the desired properties for a signature? First of all, it has to be informative, right? If a signature does not carry enough information, it's not useful. This is clear. Second, it has to be computable. Some signature, like the maximal common graph, it carries a lot of information, but we cannot compute it. That's not very useful either. Also, it has to be trackable, because in the end, we would want to be able to analyze it and prove the correctness of our algorithm. Those are three properties that it has to signature has to satisfy in order for success. Yet another feature is generalizable, which means, well, even though we are working on this very idealized graph model, we hope the signature we pick can extend to other graph models or can work under mild assumptions. This is a very demanding property, and I think we currently do not have the luxury to actually pay too much attention to it, because we are still trying to complete the understanding for the very simple case. But that is something we should keep in mind. Okay. Now, by randomness, two pairs are more similar than fixed pairs. But there's a very serious challenge, because for each vertex, it only has one true partner in the other graph, but has many fixed candidates, right? That means the true pair has to be so good that it beats all the other fixed pairs. First of all, this requires the signal to be strong. Second of all, it means from a probability point of view, our analysis has to be good enough that for the fixed pairs, we should be able to perform a union bound. This requires some sort of large deviation type of estimates. Along this line, there are some progresses. For instance, in Barak, Chou, Lei, Shram, Shang, they counted the number of balanced trees and used this signature to match two graphs. Their algorithm works when the correlation is larger than a constant that is close to 1. But unfortunately, it's not polynomial time. It requires e to the log n square that many computations. So it's not efficient. In work with Zhongmin Ma, Yihong Wu, and Jiaming Xu, we look at the degree profile. Well, degree perhaps is the first statistic that would come to mind, but it's not that informative. You could have many vertices with the same degree, which is a sign that this is not informative. But instead of that, we could look at the degree profile for all the neighbors of a vertex. So now it's not a number, it's a set. A set potentially carries a lot more information, and that's indeed the case. We use this to match the two graphs, and this give, well, this gives you a polynomial time algorithm. This is easy to compute and easy to implement. But we need the correlation to approach 1 at a rate that is 1 over polylog. So, well, it is what it is. Now let's look at the second approach, which is very natural also, because this is an optimization problem, except we don't know how to solve it because it's NP hard. But for these problems, this sort of combinatorial optimization problems, it is NP hard because we are trying to search the optimizer in the integer space. If we can relax the solution space to a convex space, then the problem becomes solvable. So what we first do is we can do some convex relaxation and solve the problem, because in the convex space, this is something we can compute. But of course, since we have enlarged the solution space, the optimizer we found is not the one we are looking for, could be very different. And there is a very common procedure employed widely in computer science, which is the rounding procedure, which hopefully can turn a fractional solution to a integer solution that one aims for. So this is also a very natural approach. And Fan Ma Wu Xu, they wrote a couple of very nice papers, analyzed some procedure along this line, and they showed that indeed this can work. This is, first of all, this is a polytime algorithm, and this can work if the correlation approaches 1 also at a rate that decays polylogging, that decays polynomial in log n. Yes, okay. So that's, roughly speaking, the situation up to 2021. And there has been more progress in the last 30 months. First of all, Mao Ruderson and Tikhomirov in 21, they made a breakthrough. They found a polynomial time algorithm. This is still based on signature and actually based on some partition trees. See, in the first counting tree algorithm by those 5 authors, it is quasi-polynomial. The algorithm is quasi-polynomial because they count the number of too many trees. There are e to the log n squared, the many trees you want to count. Then this requires too much computation. What MRT did is they build some sort of partition tree, and as a result, the type of trees they need to count is reduced, which accelerates their algorithm. So they can successfully match the 2 graphs if the correlation is larger than the constant that is close to 1. I also need to point out they need some assumptions on the edge density of the Auto-Shuyang graph, which I'm not going to report the details. And then Ganasali and Masolia and Lalarge, they analyzed the case when the average degree is a constant. So this is based on some sort of message passing, and they analyzed how to match 2 correlated trees. For this, they find a polynomial time matching algorithm, partial matching algorithm, because in this case, there's no way to exactly match 2 graphs. You have a positive fraction of isolated vertices for which there's no way you can match them correctly. And they say partial matching is possible if the correlation is larger than square root of the Otto's constant. Otto's constant is around 0.3383. Basically, if you count the number of unlabelled trees of k vertices, it grows exponentially. The rate of growth is given by the Otto's constant. And very recently, Mao Wu Xu Yu, they found a polynomial time algorithm when the correlation is larger than, again, square root of Otto's constant. Their result covers the whole regime. Basically, in order to be able to exactly match two graphs, the graphs has to be connected. This holds some lower bound on the edge density P. As long as that holds, and as long as the correlation is larger than square root of Ortho's constant, they have a polynomial time algorithm to match the two graphs. So this substantially improved the existing work. And their work is based on a carefully curated family of rooted trees called chandlers, whatever it means. You don't have to pay attention to the details. So from these works, from the previous two works, perhaps one would wonder whether this barrier around square root of Ortho's constant is exactly the computational barrier for this problem. And this leads to the next work I'm going to tell you. This is by Zhangsong Li and myself. We don't give you a definite answer yet, but we give you a strong evidence that there is no such barrier. So I will tell you what we did. For the graph matching problems, we can view this as two correlated matrices, except that these entries are correlated Bernoullis, right? If we change that a bit and look at correlated Gaussians, this is also fine, should be in the same universality class, but a bit easier to analyze. I will also tell you why it is easier to analyze later. And for this, suppose now our model is two correlated Gaussian matrices. We show that there is a polynomial time algorithm that matches the two matrices as long as the correlation is non-vanishing. So as long as the correlation is larger than, say, 1/billion or any fixed constant, there is a polynomial time algorithm that can do the job. And so there is no such barrier. And we feel this is actually the best possible. Namely, our belief is that if the correlation indeed goes to 0, then there should not be a fixed power polynomial time algorithm that can match the two graphs. Of course, currently this is a belief, but that seems reasonable. Now let me tell you some of the new features in our algorithm. I think this is actually there's something nice. The algorithm is iterative. I think we have seen typically, I think most of us, or even all of us, have seen iterative algorithms, right? It shows up so frequently and so it's used so commonly. Usually in iteration, we have a target, and as the iteration moves, we converge to the target, right? Then the algorithm succeeds. In our algorithm, it's a bit different. Our iteration tries to build a pair of vectors that stores signals. The new feature is that actually the dimension of this vector is growing quickly, but the signal carried in each coordinate decreases. And overall, the increase beats the decrease. So cumulatively, we get more and more signal as the iteration continues, and eventually we'll have enough signal to just complete the matching. I can also tell you a little bit how this iteration goes. Say at the very beginning, we have no information. We can just use for each vertex, we just compute the sum of Gaussians neighboring to this vertex and use this as the signature for this vertex, right? Now we can build many pairs of sets. Say, okay, if this Gaussian, if the sum is in some interval, this is a set. We have a set on the left, we have a set on the right. Due to the correlation, these two sets should have larger overlap than if these two sets were independently sampled, right? So each of these sets are built had some signal. Now, since we have many pairs of sets with the signal, we can try to build a vector that are correlated for each vertex, because we can now take any pair A and A prime. We look at the sum over A for vertex on the left, and we'll look at the sum of edges over A prime for vertex on the right. And each of this pair of sum give us some information, and we can use this to get a even larger number of pairs of sets, but the correlation for each pair decays. This is the idea. Okay, if you didn't quite get the details, it's fine, but just remember there is this feature that we are building a pair of vectors. Each coordinate is a set, and the number of coordinates grows quickly, but the signal carried per coordinate decreases. Overall, the accumulated signal we obtained is growing, and at some point we have enough so that we can just complete the matching in the next step. That's the rough idea. Once you have this belief that this should work, then you have to do a lot of hard work, and you also have to tailor the algorithm a little bit so that it's easier to analyze. The analysis is actually, in my point of view, quite difficult, and this is why related to why we need to assume Gaussian. The difficulty, as I mentioned earlier, is lies in the correlation among different iterative steps. So what we did in previous steps affects what we see in the future for the graph. What is worse, since the two graphs or the two matrices are correlated, what we did for the matrix on the left also tells us something on the right-hand side. And this is something very hard to control using algorithm, because a priori we don't know how these two matrices are matched with each other. So this poses, in our point of view, some major difficulties. And one way to solve this, like in many other cases, for instance, in the work of Bayati and Montanari, they use some sort of iteration, approximate message passing to solve some compressing thinking problems. There's something very similar here. We want to turn this conditioning into conditioning on linear constraints of Gaussian variables. And now you see why Gaussianity is useful, because conditioned on linear constraints of Gaussians, the remaining things are still Gaussian. We just need to find out what's the projection into the space we condition on. The additional challenge in our model is, in previous questions, usually there's only a single matrices. There's only a single matrix, but here we have a pair of correlated matrices, so there are some new challenges due to this feature. But anyway, if we have the help of Gaussian, things can be done. So now, the next order of issue is whether this can actually extend to Bernoulli case. That is to say, the Shuyang graph matching case. I think a reasonable belief is that they should be in the same universality class, but there is substantial technical difficulty. For instance, the work of Beati and Montanari, I think it would be very desirable to prove that prove some universality for it, but it's not done yet. I don't think it's because of the lack of interest. I think there's some real difficulty there. So for us, we have there's a little bit difference for our algorithm, because we could try to weaken the signal a little bit by some artificial procedure and do some smoothing so that we get something that is more looking like a Gaussian, but still there is a lot of difficulty. One can try to use the central limit theorem in high dimensions to say that, well, since we typically sum degrees, right? We look at the degrees, it's a sum of the Bernoullis. So you imagine there should be some central limit theorem. Actually, the transportation distance between these degrees and this corresponding Gaussians, they can be controlled. But what is difficult is we do not have a conditional version of central limit theorem. We do not know, okay, conditioned on linear constraints of this Bernoullis, the conditional distribution of some other sum of Bernoullis look like Gaussian. This is something we don't have. And this, in general, is not true either, I think. So we have to be very careful for this. It's probably possible, but we are still we're still working on it, and that's the situation. I think now at this point I explained what we rigorously proved and what is our belief and what is the difficulty. I don't think there's anything better I want to tell you on this. Finally, I think this algorithm could shed light on many other matching problems too, because this sort of iteration seems to be new. And for instance, if you want to match not graphs, but we could have many Gaussian vectors, they're correlated, and you want to match them. For this type of problems, there's a broad class of problems with many applications, and this potentially could be useful, but we still need to look into that more carefully. Now, I'm almost run out of time. So, do I still have time, or I should stop here?
Maybe you can take another 5 minutes, but maybe not more, if that's okay.
Okay, yeah, 5 minutes is more than enough. So let me just tell you yet another question that is of interest, which is, because we believe there's a regime that from information point of view, we can recover the matching, but we don't believe there's an algorithm that can do it. So what are we supposed to do in this regime? Ideally, we want to prove that we cannot have an efficient algorithm to do it, right? But a proof is just too much to hope for, because, I mean, for complexity theory, these are usually studied by computer scientists. Usually these are for worst case instance. And now we want to look at the complexity lower bound for random instance. It's much harder, because if you want to do reduction, as usually have done by CS people, it is usually very difficult to keep track of the change of probability measures when you cook up gadgets to turn problem A into problem B. Unless problem A and problem B, they look very similar to each other to begin with. But those are very special, right? There are some examples like this that success has been obtained. But more generally, this is very difficult to achieve. So another possibility is to show, okay, if we can show a wide class of algorithms that has done very well in many other problems, cannot solve this problem, right? That give you evidence that the problem at hand is difficult. None of this is a proof, but it gave an evidence. Or, okay, if we know problem A, or we believe problem A is difficult, and problem A had certain structure property from a probabilistic point of view, and if we can show problem B exhibits the similar type of structure, then it's reasonable to think problem B is difficult to compute. The overlap gap property is one example that has been used and that has been, I think, fairly well accepted and currently actively studied criteria to certify difficulty of computational hardness on random problems. And for this, I will just, I think I will just finish my talk with this last problem. I mentioned the motivation earlier between the Twitter and the LinkedIn, right? But suppose now we want to protect the privacy. This actually motivates a very good question. We could try to very slightly perturb LinkedIn so that on the one hand, if you use it, you don't feel the difference because the perturbation is small. But on the other hand, if you can show after perturbation, there is no efficient algorithm, or you give evidence that there's no efficient algorithm that can match LinkedIn and Twitter. That serves to some extent the purpose of privacy protection. And there are two separate issues here. One is to design a mechanism. This is not easy. This is not obvious. Two is to prove after this, you actually have a complexity lower bound so that you can protect your data. And of course, you want to achieve this by a minimal amount of perturbation of your original network. That is the main challenge here. So with this, I will just finish my talk here, and thanks for listening.
Thanks very much for a fascinating talk, Jian. Can I
Thank you.
Anybody who has any questions? Mickey.
Oh yeah, thanks, Jian, for the great talk. So you're saying that there's no information computation gap in say if so Otter's threshold is really not the computational threshold.
There is a for the matching of correlated graphs, there is an information computation gap, as we believe.
Okay.
Because if the signal, suppose P is n to some minus alpha, if the signal is like larger than some negative power of n, there is enough information already.
Okay. But so let's suppose that, you know, so S is just a constant epsilon.
I see. If you mean if the degree is constant,
yeah. So
then I think the square root of Otter's constant is probably the truth. Yes. If it's indeed that very sparse case.
But suppose you're above. So suppose so S is a constant and the intersection graph is connected. So you're above the connectivity threshold. So
the intersection of the common graph.
So suppose that, like, you know, S is epsilon, but you know P is like polylog n over n.
I think this you would not be able to. Okay, now you are getting a bit subtle. If P is polylog n over n and correlation is epsilon, I'm not sure you can do anything. I think when I said, okay, I should be careful when I said for any fixed epsilon, I'm assuming that P is n to minus alpha, and alpha is strictly less than 1.
Okay.
Thank you for catching me for that. Yeah,
okay,
I was thinking of that.
Okay,
yes.
Okay.
If it's very sparse, if it's very sparse, say constant degree, then it is possible. I think it's probably even known. Partial recovery, the threshold is given by the square root of Otter's constant. I don't know to what extent this is complete. There are various papers by this.
Okay, and okay.
Sorry, go ahead, Mickey.
So yeah, there are these various simulations that, you know, you've probably seen these papers that they kind of also have this Otter's threshold as some kind of showing that it might be some kind of computational.
Yes.
So, but that's in the sparse case. Because it's a sparse. Okay. I see.
In a sparse case, I think it's probably proved. There are 3 papers. If you put them together, it's probably known. Yeah, for the partial recovery. I was more thinking that if the degree is larger than some power of n, then this is the case that is. There is still a computational phase transition. It's just the barrier is not given by the Otter's constant.
Got it. Thanks.
Jeff.
Thanks for the clarification.
Yeah, I had a question. Well, first, thanks for the very nice talk. So I had a hardness of approximation question, which maybe I missed it and you discussed it, but I don't think so. So one version of the concrete question would be, does there exist a polynomial time algorithm with the property, if you feed it any 2 graphs, it will give you a permutation? Well, what you said in the first slide is it's NP hard. So we know there's no permutation that gives you the maximum. How about if I want to get just something which gives you 30% of the maximum thing? And then if not 30, 20, and some of these problems, I think there can be a phase transition depending on what percentage. Do you know anything about this?
I think the community knows about it, but I cannot remember and I cannot quite think from the top of my head. Something should be known whether up to some constant is possible. But I didn't. I don't know whether I ever checked the literature for this. I don't know. I don't even know. Sorry about it.
Yep. Thank you.
And then finally, I think Alex has a question.
Yeah, so I wondered about the sort of asymmetric version. So then you've got G0, which is your sort of ambient graph, and then you're sampling to random subgraphs of G0. So you could do that with different probabilities, but also one extreme case would be you have G0 and then a random subgraph G1, and you're given G0 and G1, obviously permuted. Is that much easier? Does it make a big difference? I mean, somehow the difference is that you do have some local information that tells you you've made a mistake. So when you have,
I'm not sure I understand your question. What is the model you want to propose?
yeah, so you're given two subgraphs, G1 and G2. What happens if one of them is a random subgraph, as it is at the moment, and the other one is the entire graph?
Yeah.
So
I see. You mean, what if the edge density are not the same in these two subgraphs? Do you mean what if the edge density are not the same in these two subgraphs?
Yeah.
Okay, good question.
Well, also, I think what he more specifically said is that what if you take the parent graph and one of the subgraphs?
I'm interested in both questions.
Oh, I see. So this should only be a bit easier, right? I mean, this should not be harder because you can always subsample one from the mother graph. Yeah.
Okay.
You should be able.
I'm wondering if it's much easier because. So the point is, when you have G1 and G2, the model that you have at the moment,
right? I guess this question is only relevant.
That the other one doesn't.
This question is only relevant if the average degree is very sparse. It's like a constant, right? Because otherwise, as long as the correlation is non-vanishing, you have a polynomial time algorithm. So more or less, they're the same. You could say if. Yeah, you could say if this, you could say if there is an asymmetric case and you are very near the autos threshold, but above it, whether you can solve the problem, right? In the very sparse case, we know potentially there's this threshold given by autos constant. But if you are slightly above it, but asymmetric, what will happen? I think one has to do computations. I believe the method should work, but which answer it gives, I didn't compute it myself. It has to come out from the computation. I think one just follow the method. It should give you something that's.
Okay, I'm not. What I was wondering was whether if one is a subgraph of the other, then there's local information that tells you that I've definitely made a mistake here, which you don't have in your version of the problem.
Wait, how do you know that you definitely made the? Oh, I see.
Because one is actually a subgraph of the other. So
I see. Yeah, I'm not sure that would help you so much, but I cannot be sure. Okay. Well, basically what you said is you just know some bad matchings, you know for sure it's a bad matching. Yeah. But our job is not to, our job is not to rule out some bad matchings out. So I'm not sure it actually, I don't believe it helps that much. I believe we should follow the same analysis and whatever comes out of it should be the answer. That would be my best guess.
Okay, thanks.
Great. That seems like an excellent place to draw to a close. Jian, thank you so much for joining us and for giving a lovely talk. I'm going to stop recording and then I'm going to invite people to unmute and give Jian a big round of applause.